So we learned about regression. The whole idea was we would like to, we found that our data is linearly correlated. It looks like a line pretty much. And we would like to extrapolate new facts about new people and stuff by reading it off the line. But how good is that line is the question for the day. So this is chapter 16. Please read that one. Shouldn't be the longest one. And kind of here's what our data looks like. When we let's say that there really is a perfect, this is the green line that is exactly what our data is supposed to be on, but it's never going to be perfectly on it because usually your data is taken from, like most things in the world we learned, are normally distributed. So like if things are supposed to be on the line with good confidence, they will be, like a lot of the time they will be, but some of the time they'll be over here on the graph, right? If it's normally distributed, it doesn't have to be perfectly in the middle. Just like if you flip 100 coins, you expect it to usually be 50 heads, right? And 50 tails, but sometimes it's like 45 heads. Sometimes it's like 60 heads. And so it's all over the place, even though it is meant to be the 50, right? So if our data is supposed to be on this line, just because it's distributed and we're in the real world, it may be a little bit off. Like the distance from this line is like randomly drawn from some distribution, where the mean is 0. So like sometimes, okay, even though it's meant to be on the line, just like due to randomness, due to the fact that it was normally distributed, like sometimes this dot was meant to be on the line, but it's like 3 points off of it. This one's like 2 points off of it in the other direction, etc., etc. So like our data is noisy. It doesn't look like it should be because the real world is a little bit random. So what we get to see though, right? We don't get to know this green line. We have no clue what the real answer is. We don't know where this green line is. We just try to estimate it with regression. We try to find the best line that fits through the points that we have. So this is all we really have, right? All we really get to see is our data set. We are trying to find this green line, but who knows where it really is. And we make the best line that we can through this data that we see, right? Through this data that we see, which maybe is something like, I don't know, what's the best line through this data? Let's try to draw it. Probably something like this. I don't know. Seems kind of right to me, and that's not exactly the green line, right? It's a little bit off, but it's kind of close. So the data that we get and the way that we extrapolate stuff from it is not going to be perfect. It's never going to be perfect because our data is noisy, because we live in the real world, things are normally distributed. We never get our parameter, right? We always get a statistic. So let me show you some code about kind of like what happens here, what this means. So I've got some sample code from the textbook. A very fun thing. You don't have to understand any of the code I'm about to paste, but I want to at least show it to you. So this is, there's the code. And then the title of this, I might as well just keep it right like that. So we're estimating stuff with regression, with linear regression, and we have no clue if that's really the line. All right, so here's some examples. So this is just an interesting function that the textbook people made, and I'm running it. So here is like randomly generated points that are meant to be a little bit off the graph, right? They're normally distributed, and they're meant to be on this line, but they're a little bit off of it because the data is normally distributed around it. All right, that's just how the real world works. So this is the true green line this data lies on. It's meant to lie on it, but it's a little bit off because of randomness, because of normalness. And so what we get to see are just those points, right? We don't get to see the true line that they really do lie upon. We don't get to know the ground truth. And so we get to see just the points that we make some sort of guess, right? We use what we have. More points, the better. The more points we get, the more likely we're going to get at this true line. But we draw the best line that we can through this data, and it looks like this. All right? This is our estimate of the true line. It's not quite the same. It's like this is the best line that comes through the points that we have. That's all we can use. All right? And so the regression line and the true line are going to be a little bit off. You see that? They're a little bit off, but they're kind of close. The more points you had, of course, the better you'd have this estimate. And so, yeah, that's kind of how the world is working. So like the data maybe really does lie on a line. It is perfectly meant to be there, but we know that we're not always going to get 50 heads. It's going to be a little bit off. It's maybe normally distributed off the line a little bit every time we take a reading, and we get to see the points only. But we can give the best line through those points through what we have. But the question is, how close will it be to the true line that the data is meant to lie on if it really is a linear relationship? All right. So that is where we're going. Okay. Let's see. Yeah, I want to show that too. So again, that's all we get. So we do need to say some things now about linear regression because, okay, we never get the true line. What does it do for us, really? So here are assumptions. This is a model of linear regression. This is what we're assuming is true when we use linear regression. We assume that the data really does lie on a line. Like the relation between the x's and the y's, they are perfectly linear. We have no clue what the real line is. We just have our points, but we know it's meant to be linear. Why would we use regression otherwise, right? So we're assuming that there really is a line somewhere that our data lies on. We just don't get to see it, but it is a perfect line. All right, that's what it means. That's why we use linear regression. All right, we don't know what the true line looks like, but it exists. And the data that we have, that we plot and we find the best line that we can through it, has been generated essentially through randomness in the real world by just taking things and pushing them off the line a little bit in a normally distributed way. All right, that's what we're assuming. So like this point, this x, it's meant to be this y, but it's been pushed a little bit off the line. Pushed a little bit off the line because the data is normally distributed. Doesn't have to be perfect. Doesn't have to be exactly 50 heads for every 100 coin flips. It's a little bit off the line, but we can quantify, we can model how far off the line it usually is. All right. And they're being pushed vertically up and down randomly according to some normal distribution with a mean 0 around wherever it was supposed to be on the line. All right. So for every point that we get to see then, that we're going to do linear regression on, we are assuming, this is why we're assuming it works this way, we're assuming that every point was really meant to be on the line, but it's been pushed off by some random amount of error, just due to being normally distributed. Some people are just naturally randomly taller than other people. It's never going to be perfect, but it's meant to be, right? It's meant to. There is some true line, but it's just off due to random error. Okay, so that's the idea. Let's see. Do I want to say anything about that yet? So yeah, I want to, with that in mind, you know that if we took different points, right? We got different samples, we get different lines. Right? If we took different samples, we would get different lines, and maybe they'll all be a little bit off of the true one, right? Maybe they'll all be a little bit off of the true one. So we need to talk about that. So we only get one sample again, usually. It's very costly to take another, but we want to think about now, and the boot is exactly where we're going with this. So if this was our data, something like this, like this, these were the good points that we spent so much money on getting. We drew a line through it all. Like this is the best fit line through this data. But what if we went out and we got more points, right? We'd probably get different data for sure. If we sampled our population again, we'd be asking different people facts, right? Different facts from different people. And we'd get another best fit line through that data, wouldn't we? And it might be a little bit off. So if we took new data, we might see new relationships. It's not the same. We get a different slope, we get a different intercept. Probably be close if we took enough, right? It's meant to be approaching some true underlying truth, but we don't know what it is still. So if we took more data, if we took another sample, we get another best fit line through that data. Again, we don't get to see the full picture ever. So our question now is, how in the world can we be accurate? Like how accurate is the line that we just made, the first one? Because that's the data that we had. How close is it to the actual secret green line that represents the population, right? So if only we could get more samples, then maybe we could like average together, right? All the slopes and all the intercepts, and that would get us a lot closer to the true answer. But usually it's very costly to go and get more samples, but we know how to make more samples without getting more samples, don't we? We can bootstrap. So that's what we're going to do again. So this comes back and helps us out And essentially our goal is, because we can never know the true line. We can never know the true line. It's a little sad and philosophical, but we can never know the true slope and the true intercept through our data because we don't have all the data ever, right? We don't know the true relationship. We can only estimate it. But if we bootstrap, if we do this enough times, we get enough different looking samples, it'll more and more likely, it'll more and more represent the population at hand. And then we can maybe get an interval for what the slope should be and an interval for what the intercept should be. Yeah. A confidence interval for both of them. That's where we're going. Does that make sense? That's what we need here. That's as good as we can do. We can't have the actual answers, but we can get an approximation of a range for the answers. Okay? So we can do that again for this time, not like averages and sums and things, but slopes and intercepts. So we can use this for regression. So yeah, we can bootstrap our sample data. So here is our original data. You know what a bootstrap is. We sample with replacement so that maybe if our original sample, we didn't ask enough old people things, it'll randomly clone some old people and it'll look more like the actual population, or vice versa for young people. So we get a bunch of different looking samples that is similar to our original one, but often a little in different ways that are more and more on average indicative of the population. So cool. That's our goal. Bootstrap to get more predictions of our regression line and more slopes, more intercepts. And we do that enough, we can have 1,000 different slopes, 1,000 different intercepts, and we can get a 95% confidence interval for what should the true slope be? What should the true intercept be for the regression line? So that's the goal. That's where we're going, and I want to show you that. So let's do this for our example from last chapter. So this is regression prediction. That's the title of this chapter. So we're using regression. We get one slope and one intercept when we do regression, but we want to predict a true line for our data. Okay, so let me just steal all this code from last chapter because we need it all. We need to be able to convert things to standard units, correlation values, the slope of a line, of our best fit line, the intercept of the best fit line, fit the values for the x's and the y's, and then the residuals of what was the error after we make predictions. So we need all those things. So bring them all in, and then let's use the birth weight example. Let's see here. So this is the baby table. So this was our smoking data set, and we had a bunch of different numerical data on mothers and their children, and this time let's do how long, gestational days, how long the mother was pregnant, and then how, I assume this is probably in ounces, or I have no idea. Yeah, I assume this is the birth weight of the baby. How much the baby weighed, probably in ounces. So that would make the most sense to me, because 120, because it's is it 12 or 16 ounces to a pound? That's 7.5. That makes sense. Okay, cool. So that is, let's look at that, because that is going to be nicely linear. Because if you can imagine that if the mother was pregnant for longer, the baby had more time to grow, and it would weigh a little bit more. So there's a decent linear relationship here if we look at it. And it's a pretty steep line, though, interestingly enough. So here's our data set, and you can kind of see, all right, the longer the mother is pregnant, the more gestational days, the heavier the baby is when it's born. And we can check for correlation. What's the correlation of those things? So let's make sure it's kind of linear. Correlation on the births table for gestational days and birth weight. There are a bunch of points in weird places. You can see kind of it's very packed around 9 months, of course. Everywhere else, it's a little dots are all over the place. So this is decently linear, 0.4, not perfectly linear, but let's zoom in on the data that's not extreme, too long or too short, because we'll get a better linear relationship if we cut off the data So here is some data that the book is telling us. According to the US's CDC, this is how long a preterm pregnancy is less than 37 weeks, and a post-term pregnancy is more than 42 weeks. So we'd like to cut it off with between these days. All right. And let's look at the data where the gestational time was between that many days and that many days. Where these values are between 259, 294. So that's that data. Let's just call that the birth table. Or we can go a couple weeks outside of that. So I think the 225 and 325 is what your book used. Let's call that the births table. And then if we scatter on it now, this is more linear, right? You've got some outliers because of like premature births and things like that that we've kind of cut off now. These are like normal amounts of times to have a child. And so now if we check the correlation, it's a little bit better. So it's like 0.43. So it's a little bit more linear this way. And we can look at this. We can get the fit line. Like, what is the best line that runs through this data? We can try to make some prediction. So based on how long you've been pregnant, how heavy is your baby going to be? And so here's the line. We can calculate the line with our functions as well, though. But like, that's a decent line through the data. And again, our goal, we're trying to infer, right? We have no clue if this is the right line. This was just the best line through the data that we had for the mothers that we took a survey of, right? Maybe this was at one hospital. Who knows? Are these representative of all babies ever? Maybe not. So goal, can we estimate? Can we get, if there is a line, maybe there is, it probably is, can we estimate it? Can we get a better estimate? Because it's probably not exactly this one, right? Can we estimate the true relationship between X, which is gestational days, and Y, which is the birth weight of the baby? We'd really like that. And so right now, for the best line that we have at hand, for the data that we have right now, the slope of the best fit line, we ask for it, births, where we're using gestational days to predict birth weight, is 0.53-ish, 0.54. We can do the same for intercepts. But is this the true slope is now the question. Probably not. So what we'll do is we'll do everything we did before for bootstrapping, but this time we're going to calculate not like an average, not like a sum like we did before. Like those were our normal statistics from before. Now we're going to take a bootstrap sample, predict the slope of the best fit line through that sample. Yeah. So we get another sample still, but this allows us to get a better estimate each time, a different estimate each time for the slope of the true line that should go through this data if it's really linear. Okay, we're assuming that it is. We're assuming it matches our linear regression model. Cool. So let's try it. Does the process make sense for what we're about to do? We want to try to get the true slope of this line. Like this is the line that's through this data, but who knows if that's the real one. So let's take some more samples by doing bootstrapping and get a bunch of slopes. And then we can calculate a confidence interval. Okay, so let's do that. I think it would be useful to type it all out. There's a lot of typing that I have to do right now. We're going to do it all in one cell, but I think it'll be worth typing it. So let's say, let's do 2,500 samples. So repetitions. Let's calculate 2,500 bootstrap samples. So we're recreating our survey 2,500 times, getting some new looking samples, and we can get the slopes for that, right? And get the slopes for those guys and add them all to an array, just like we did before. So create 2,500 bootstrap samples, find the slopes, and save them all. So keep them all together so that we can calculate a confidence interval for them. So for I in np.a range, that many repetitions. And you can change this, but my computer is slow enough for 2500 to be plenty. So let's also keep track of those slopes. Let's make an array called slopes. It starts empty. Because we're going to get a bunch of different values that are kind of close to this one, but will be fluctuating. That's the whole point. And we can see how accurate it was. We can get a better, we want a range, because we can never know the true slope. So here, all right, every time we're in a repetition, we're in the body of this loop, we want to calculate a bootstrap sample. So give me a bootstrap sample, please. Bootstrap sample. So use my sample to calculate a new sample. So that's my births table. If I just sample from it as many things as are in it with replacement, those are the defaults. So I just say sample by itself. That will give me a bootstrap sample. I have sampled with replacement as many things as were in the births table. So now I've got a new looking sample that's slightly different. It's cloned some people. It's deleted some other people. All right. Cool. And so for that new sample, let's get its slope. So not for the births table anymore. I want to get the slope of this bootstrap sample table. So the process coming back to us is we're just doing what we did before, but now for slopes, not for like medians or averages or things. So get that guy, and let's call that bootstrap slope, right? So now I have that slope, and I want to keep track of them all, so add it to the slopes array. So I could be like np.append to the slopes array that new bootstrap slope, and put that in slopes. And so now after this loop is over, I will have a size 2500 array of a bunch of different slopes that are not quite this, right? Sometimes it might be exactly that, but not very likely. So we will have a bunch of slopes, and now we can get a confidence interval. Like what 95% of the time, what should the slope be? And that will give us a good estimate of the true underlying slope for like gestational days, for the relationship between gestational days and birth weight. So yeah, that's our goal now. So we have the slopes array. We want to get a confidence interval. Let's do a 95% confidence interval. So find the endpoints of the 95% confidence interval for the true slope. And so the left side is going to be, if it's a 95% confidence interval, you want it in the middle. 95, there's 5 left over, and so you want to kind of like put 2.5 on each side. So the left side is which percentile? It's going to be the 2.5th percentile for the slopes array, and then the right side is going to be the 97.5th percentile, right, for the slopes array. And so this will give me the lower half and the upper half of the 95% confidence interval for that slope data. So we're approximating what the slope should be, right? Cool. Our original slope was this one, this 0.54-ish thing. Let's keep track of that too. Let's save it as a variable so we can print it out all together. This was our observed slope from our original data. Observed slope. I did not spell observed right. I have to start over. Observed slope. There. That's the slope we found in our actual data. It's going to be somewhere within this this range, probably going to be in the middle, but that's beside the point. And yeah, this was the slope of our original data. Slope of the regression line from the original sample. We observed it, and then let's just print out all that stuff together. That part of the code I don't care about you understanding, so just a bunch of prints and make some tables. So here's that code. You can look away if you want. This is just like displaying the results. You don't have to understand this code, but everything above it you have to understand. So this is just gonna do the whole thing, plot it in a nice way. It'll tell me the slope of the original one, and then it'll show me the confidence interval of the true one, so like the left and the right side together. Cool. Boop. If I typed it all correctly. It takes a while to do the 2,500 things because it's a decently large table. But hopefully, if I typed it right, it will end up happy. But does the process make sense to us? Are there any questions before I explain what just got printed out? Does the process make sense to what we just did? It's just like one of the previous chapters where we learned about confidence intervals for the first time, where we were trying to like, all right, figure out what is the true population median of this data? What is the true population average of this data? We don't know. We can only do sample stuff. So if we get enough samples, though, we can calculate confidence intervals. We did bootstrapping to do that. So again, 2,500 times we made new samples. We did what we wanted to do for those new samples, calculate the slope of our regression line. So what do we think it should be? Well, it's probably not exactly what we found for our original data, so we got some new samples to figure that out. We added them all to one big array, so now this array has 2,500 slope estimates in it. And we took percentiles to gain a 95% confidence interval. So in our answer, left and right, they're the range where we can say we are 95% confident that if we did this again, we would see the true value within this range. Okay, so that's pretty cool. So here's what got generated with the table and everything. So the original slope of the regression line was 0.538-ish. And for our 95% confidence interval, we're saying that based on the different samples that we could take in our bootstrapping process, we're saying that 95% of the time the true slope will probably lie within this range, which is a decently big range, honestly. So maybe we needed more data to like lock it in, but that's what happened. And here's a graphical representation of that. You can kind of see it. Of course, it's going to center around the original one, this histogram, and these are all the different slopes that we generated using bootstrapping, right? For all the different samples that we calculated, these were the different slopes of the regression lines through that data that we saw. And here is our 95% confidence interval. So to be 95% confidence, we have to have this wide range through this data. And the slope of the regression line could be like 0.45 all the way to 0.6 something. So it's like a decently wide range, maybe. We're not sure yet, right? So maybe we want to get more data for more mothers to try to lock it in, because you know that the more data you get, the tighter that confidence interval gets squeezed, right? But that's what we found, all right? That's pretty cool. That's the process. So now we're using bootstrapping to not just do like average and median stuff. We're using it to calculate other things that we care about, like using it for prediction. It's pretty cool. Any questions about that process? Because this was just for the slope, right? We could do it for the intercept too. We don't know what that should be. Let's get an estimate of what the y-intercept should be for this to try to use gestational days to predict birth weight. So this was all this stuff. We did it just for the slope. We can do the same stuff for the intercept. So let's see. What do I want to do? I guess I could turn this into a function first, and then we could easily change it, maybe. Let's see. Yeah, I guess before we get there, let's stick with slope for a second. I do want to show you some cool things. I guess maybe that could be an exercise for you. So instead of just saying slope all over the place, get the slope, you could have said intercept here. That would have calculated the intercept. So yeah, that's pretty nice. Oops. Sorry, somebody's trying to call me. One thing that you could do, if you want to do this again, you know it's going to be a little bit different. So if I reran all this, I would get different confidence intervals because I would like randomly generate new samples, right? Randomly generate new samples. So let's run it again, but let's make a function to do all this really quickly. So here's a cool way to do this. What is this process? It's like using bootstrapping to generate a slope interval, confidence interval for the slope. And we could use this for it doesn't have to be for the births table. We'd be like, all right, for some table called T, give me the X column, give me the Y column that you're using to predict from the X, and then give me how many repetitions you want to use. And now I don't have to say repetitions equals something. I can make a function to do all this process all over again for any table. That's kind of neat. And I don't know if your book has shown this to you or if I've shown this to you yet, but this is how you get the default, right? You don't give repetitions, it'll be set to 2,500 this time. And yeah, let me show you. Let's clean this up so that we can do it for any table. So not for any, not for births, for table T. So this is a function that we could call and we can get it really quickly for whatever our table was. So sample from the table T. It wasn't gestational days anymore. It was X. It wasn't birth weight anymore. It was Y. Whatever we wanted, right? Whatever we wanted. And that's all general. Still 95%. Observed one. That was our original slope for the table T for X and Y. And I believe, do I say births or gestational days, birth weight anymore? I think that covers it. So this is like generalizing what we just did. So you can get this really quickly for any table now for what we just did. I think in theory I didn't forget anything. So now you can just call it. It's like, all right, you need a bootstrap slope at a 95% confidence interval for a bootstrap for a slope of a best fit line. Do it for the birth table, do it for gestational days and birth weight. And you can ask for more repetitions if you want to. Like by default, you say nothing. I just call it right now. It'll give me 2,500 repetitions. But if I say, you know what, 3,000 this time, it'll do 3,000. That's pretty neat. So this is just a quick function now that we can use to calculate some slopes. And again, it will take a second. But we'll notice that we'll get some different answers. Somewhat different answers. So this one, again, the original slope never changed, but the 95% confidence interval this time was 0.459 to 0.62. Decently close, but still a little bit off. That's pretty interesting. So it's you run this all over again, you get different answers, right? So maybe, but the more you do, the more repetitions you do, the more this becomes like exactly what it should be for your original data. Cool. Yeah, let's see. What else do I want to say? So again, does the process make sense? So for any table using X to predict Y, you assume that there's a linear relationship between them. What is the slope of the best fit line through all this data? Well, we can use bootstrapping to go and figure that out, to go and estimate it, right? To get a confidence interval of whatever granularity you care about, maybe 99% if you wanted to. This one is just 95. That's a common one. And yeah, we're not sure, but this is what we got. Yeah, so if we're good, let's say, let's use this now. Here's kind of our goal, right? Again, we have all of our original data. Let's go back to the scatter plot. We've got all this data, right? We have, here's the new data. Here is the data that we have for all these mothers in our data set. We're not sure, right? We're not sure if our best fit line is great, so that's why we are using this confidence interval stuff. If we took another sample of mothers, we get some new data. So again, that's why we're using confidence intervals and bootstrapping. We are using, the whole goal of regression, right, is for prediction, right? So like you give me somebody, you say that, all right, the estimated due date for this mother is 280 days. The whole point of using regression is to find the line and like read off, all right, how heavy is the baby going to be on that day? So if we're not sure about the slope of the intercept, again, we're not exactly sure about the weight of the baby, are we? But again, we can make an interval. We can give back a prediction interval, all right? So that's kind of the goal. That's why we're doing all this, all right? So our goal for regression is to predict. We've noticed that we can't have the accurate answer, so the best we can do is get a range of answers. Predict a confidence interval. This is our goal. When we're using a regression, this is usually what we want, right? Predict a confidence interval for someone who's not in the sample, right? We have the estimated gestational time for a new mother, and let's tell her how heavy we think her baby is going to be when she gives birth. So we have data for, I don't know, let's say that we want to predict somebody how heavy a baby is going to be for 300 gestational days, something like this. So 300 days. We have data for all the women who had a baby around 300 days. but some of those babies were heavy, some of those babies were light. It's not perfect, right? So it's kind of all over the place, a little bit at least. There's no right answer, but maybe it's normally distributed around the right answer. That's our assumption. So we have data for 300 gestational days, but it's all over the place. And that data that we have was only for the mothers in our sample. You go to another hospital, maybe you have different facts, like they put the women on different diets or something. The doctor suggested different things, who knows? But it's all over the place and only for the people in our sample. So we're assuming that our sample is relative to like the entire population of the world, but you never know. So let's do a bootstrap to see how our prediction changes for 300 days exactly. We want to know how heavy a baby is going to be at 300 days. Okay, let's do a bootstrap to see how the prediction changes. So let's make a quick little function to like make a prediction. So give me a prediction at a certain place. So you give me a table T, we're using X to predict Y, and you give me an X value at which to make a prediction. All right, that's our goal. So let's actually write a docstring for once. So T is the table we're trying to make predictions for, our birth table in this example. The X is the label of the X column that we're using to make a prediction for the Y. The Y is the label of the Y column. We're trying to calculate the best fit line through, right, and make predictions for eventually. Like that's the data we have. And then the X value parameter is the X value for which we want to predict. So read it off the best fit line through everything. So, all right, if we want to make a prediction with regression, we just, well, we do our mx plus b for that x value, right? So we take, we return mx plus b, m times x plus b. But what is m? M is the slope, right? It's the slope for that table using x to predict the y, right? And the x is the x value that we're passing along here, right? And then the b, what is the intercept? Well, we can calculate that. The intercept for that data, for that table, using those x's to predict that y. See how that is our prediction using linear regression for this particular x value, for this particular table? So it's long-winded, but that's the idea. And so our prediction for our original data set at x equals 300 would be calling this function for the births table using gestational days to predict birth weight. That's the x, that's the y for our original data set, right? Give me the value at 300. I'll call this prediction at 300 days, because that's what we're trying to estimate, right? So what was that? For our original data set, read it off the line, it was about 131 ounces for the child, okay? And that's our prediction. But we know, again, this is just an estimate. This is the data that we had at hand. If we took another sample, right, we would get another varying prediction at 300 gestational days, right? So the question is, like, we want to give an answer to this mother, right, who's planning on having a baby at 300 days. We can give her a range. We can do some bootstrapping. We can give her a range because different samples are going to have different estimates, yeah? Different samples are going to have different estimates. And let me show that to you really quickly with some code that you don't have to understand, all right? So again, this is just some fancy code that's going to help you understand the process, but you don't have to understand how it's generating it. So here's just like, here's a bootstrap process one more time. So this code, what it's about to do is it's about to make a bootstrap sample of the births table, and it's trying to predict gestational days all over again. Oh wait, no, this is for the original, right? This is our original data set, and here is 300 days, read it off the line, right? That's our 130-ish, right? There's our answer for the original data. But if we took a bootstrap sample, we get a different estimate for the data. The line would be in a different spot. It would be like a little bit above, a little bit below. We read it off. At 300, it would be a different value, right? So let's do 5 bootstrap samples. This is a cool code you don't have to understand. Just making a bunch of figures at once. It's really cool. So here's this. Boop. Let's take a little bit. Isn't this fun? So here's like bootstrapping visualized. Here was our original data set. When we took a bootstrap, some things are getting cloned, some things are getting deleted. Like this dot, it's not there anymore. See it? So that one got deleted. Some things are getting like cloned a couple times. That's the whole point, is trying to make another sample that's similar to your original one, but slightly different to maybe better reflect the population. Do this enough times, it better reflects the population. Assuming your original sample was a good sample. Like here's a bunch of different bootstrap samples. You can see that they're mostly similar yet slightly different. And so the best fit line through all these guys is going to be a little bit different, right? And so let's say we did 10 bootstrap samples and we try to get the best fit line for that data. And we try to read off the line at 300 days, right? We get different values. You see how, like, just like zoom in at 300 days. Like, look at these guys. Here is the range for 300 days for this data set, from here to here-ish. For this other data set, you see like 300, like from here to here, like a little bit squished. That's good. It might be expanded for other ones. So that's the idea. So again, this is just some fancy code to show you the point of all this. So let's say we took 10 bootstrap samples instead of just 5. We took 10, and we try to get the best fit line through the data for those 10 samples, and we read the value off at 300. Here's what we found, all right? If I run this again, I get different lines, of course. But for my 10 bootstrap samples, here are the best fit lines through all that data, and here is the answer at 300. You see how it's going to vary? We're not sure what the true answer is because it depends on the data that we have. We don't have the true data on like how motherhood works, right? So all we can do is estimate. All we can do is estimate. And so these would turn into, if you did this enough times, these would turn into our confidence interval ends, right? These are the ranges, okay? So like these are all the different lines that we just generated. Like they have these slopes and these intercepts and these predictions when you have x set to 300. All these different values, all right? And that's the goal. And so if we do this all over again, right, instead of getting a bootstrap slope, we can try to do a bootstrap prediction. Do you see how the same thing is going to happen? We're still going to have a bunch of different estimates of what's going to happen at 300 days, right? We're still going to get a bunch of those guys. And that's as good as we can do. We can get in an interval, which is great. So let's make that happen. Let's try to... do I want to copy and paste this is my question. I think so. So it's mostly what I want to do, right, is I want to copy and paste this code 2,500 times. Instead of calling slope and getting a bunch of slope estimates, all I really want to change about this is call prediction at 300 days. Just get a bunch of different predictions at 300 days for each new bootstrap sample. So really just copy and paste this, change that line, call the array not slopes but predictions or something. Maybe turn it into a function. That'd be fine. So that's what I want to do right now. So here's all that code where I've already done that. I hope you kind of see what's happening. It's all that's been changed, right? For you give me a table, you're using the X column to predict the Y column. Give me the X you're trying to do a prediction at. Give me how many repetitions you want to do. And we're doing pretty much everything all over again. Just like it's a predictions array rather than a slopes array this time. But like for each time I take a bootstrap sample, I get a prediction for that table, for that bootstrapped table at that X value that I want to make a prediction for. And I just keep track of them all, and we'll do another 95% confidence interval before we print it all out pretty. Do you see the difference? There really isn't much. It's just bootstrap, get what we need, and this gives us a range. This gives us an interval. So let's do that. Let's do it for exactly what we care about. Let's do it for bootstrap predictions. Bootstrap prediction for my births table, using gestational days to predict birth weight. That is our example of the lecture, I guess. And let's say we want a prediction at 300, right? That's the next one. This is the new X, is the value you want to make a prediction at for a new mother, and who we assume is going to have 300 days of gestation. And let's do 2,500 repetitions to spice things up. All right, perfect. And this will take a while again. But again, each time it's getting a new bootstrap sample, calculating the best fit line through that sample, getting a slope and an intercept for it, reading off the value on that line for 300, because that's the special day we care about for this, this person we're trying to make a prediction for. We have all these lines and all these slopes and all these values then at x equal to 300, all these different y values, and you put them together, you get your intervals based on the values you saw. And so here's the answer. So here is our original height for the original data, is 130.81. That was how much we assumed the baby was going to weigh using our original data. But when we did our bootstrap predictions, we found that sometimes for different bootstrap samples, the weight of the baby we're predicting to be a little bit weigh a little bit less to a little bit more. So 95% of the time we're confident that the baby's weight will lie within this range. And that's a better thing we can say to the mother, right? We can be like, it's not too many ounces off, right? It's not just, the slope was kind of all over the place when we did that one. But this is only a few ounces on either end. And so we can give peace of mind to the mother in a sense. Like, all right, from the data that we have, we assume that your baby's going to be between this and this weight. That's pretty nice, right? And again, here's that in histogram form. Like, here are the predictions that we generated with our bootstrap samples. Here's our 95% confidence interval highlighted in yellow. Here's the 2.5th percentile. Here's the 97.5th percentile. And we want to be 95% confident. We got to say, like, it's somewhere between here and here. We're not sure where. So we assume that the true value 95% of the time, right, is within that range. Isn't that cool? And I think that's what I wanted to say. Are there any questions about that process? Do you see how you can just use bootstrapping, not just to predict medians and averages and things, but like regression predictions, regression slopes, regression intercepts? All right, so the last thing I want to show you before I ask you to try some stuff is, I'll give you all this code too, of course, but let's see. Let me show you something interesting and weird and kind of cool. Remember that the regression line is calculated in standard units secretly, and it's all kind of centered around the mean. So something special happens when you're making predictions around the mean, actually. So what was the mean gestational days for these women? So let's go to births.column. What was the average amount of time that a woman in this data set was pregnant for? Gestational days. It was about 280 days. Okay. Let's go to a value around 280 days. Let's make a prediction. Let's do a bootstrap prediction around that many days. Dun, dun, dun. Let's do like 285. So our original prediction was like for 300 days. What is our answer? This one is around the mean of gestational days. It was closer to the mean. Let's see what our prediction confidence interval looks like. We were off by 28. It was like almost 29, 30, 31, 32. So like 3.5 ounces-ish was our range for this interval for 300 days. For 285 days, closer to the mean, right? Here is the original height. And then here is our confidence interval height. Do you see how it's a little bit more squished? That's interesting in itself. So this was about, this one was like 2.5 ounces away from each other, this range. This range is only about 21, 2, 3. It was only about 2 ounces away from each other. So it got squished. Isn't that interesting? So it got squished because of the way regression works, in a sense. And just because of the way data works, we had a lot more data around the mean. And so it's less likely for us to mess up around the mean. So our confidence interval is actually going to be a lot closer. It's going to be tighter when we're closer to the mean, which is where we have more data. So usually where we have more data. And that's interesting in itself. So the moral of this story is that predictions closer to the mean don't spread out as much. And let me show that to you graphically. There's a really cool graphic that I stole from the book, or at least from the lecture from the Berkeley people. So again, you don't have to understand this code, but look at what's happening. Predictions closer to the mean, they don't spread out as much as predictions farther away from the mean. So 300 days versus, which is farther away from the mean, of like which was 280, and here is closer to the mean, 285. So look, if I run this again, I can get it to be a little bit more extreme. That's better. Cool. So it's like how many? So 10 bootstrap samples. What is the best fit line through these samples? They are these. Different colors, very pretty. Here's our 300-day estimates. Right, for just read off the line for bootstrap sample estimates. And then here's 285. Do you see how this one is wider than this one? It's closer. The way that the line is calculated is based on the mean, and we have a lot of data around the mean, so it's harder to mess that one up. It's harder to mess that one up. So yeah, that is that's just a cool fact of regression. The spread, your predictions closer to the mean are not going to be as far apart because usually you have a ton of data around the mean. Like here we are. Here's like the mean. You can imagine it's a really dark blue part. This part right here, it is very, very heavily accounted for. And so even if you forget somebody when you're making a bootstrap sample, like you lose one person, you still have a million people near that mean, right? You're not going to be very far off. You're going to assume that the value is still around there. That's kind of neat. I like that. So that's kind of the process. You can use bootstrapping. Moral of the story, right? We don't know the true line. We don't know the true line. We assume that it's kind of like there is a true line. The data is kind of randomly distributed around. But all we get to see is the points. We get one good line, one best fit line through those points that we got. But we can, if we took another sample, we get a different line. We know how to take new samples for free with bootstrapping, get more lines, make new predictions, get new slopes. We can get an interval out to somebody, and that is more accurate. Yeah. So that's the goal. That's the answer. And now I want you guys to try some things if you're ready. Are there any questions about what we did before I give you this code and have you try some stuff? That's the process in a nutshell. So it's just bootstrapping all over again, but what we're doing with bootstrapping is cooler than just give me a median. All right. So here, let's do this, crunch dice. Let's get started on the first one, then I'll give you all this code. So here, we got plenty of time, but what I'd like you to do is play this game all over again. We'll do it for the sun's heights data and for the serial data. So what I'd like you to try to do, you can honestly, let's see here. Let me explain myself some more. Let's do, we want to bootstrap the slope out of what? Let's use the father's height to predict the son's height, and we'll bootstrap the slope of the regression line using father to predict son, and we'll get a 95% confidence interval for the slope. So let's care just about slope. So you can kind of use the function that we made, but see if you can copy and paste the code before the function just to like get practice, I think. But this is the goal. So for the sun's heights table, please, let me read that in so that you have all the things. Table.read table, sun's heights. We have all these. I'd like you to calculate a 95% confidence interval for the slope of the regression line using father's height to predict son's height. Yeah, because we know that that's a linear relationship and that's the most correlated one, father to son. So let's do that. All right. So let's give that a try. Let me give you all this code so that you can go to the code from class real quick and get it. So yeah, now if you refresh the code from class page, you should have our chapter 16 file. You have everything that we got. So copy and paste in the things that you need. Like you'll need definitely all this stuff, standard units, regret, intercept, slope, all those bad boys. And then you'll go looking for, I think this cell where we did 2,500 repetitions. That's a good amount. You'll just change around which table we were using because you get the slope all over again. All right. We also made a function to do it, but please give that a try. See if you can like change the right values around to get what we need. But use father's height to predict son's height and get a confidence interval for the slope of the regression line, 95% confidence interval for the slope of the regression line using father to predict son by doing, let's say, 2,500 bootstrap so that you don't have to change my code. So you can delete that. And let's see how widely that varies, right? This one we have enough data to get a really good tight interval. But we don't have maybe it's like the heights within 10 inches rather than 2 inches. We'll find out. And let me know if you have questions as you're trying it, but I'll give you a head start and I'll do it too. That'll be fun. I wonder how fast it is on your computer. It's probably much faster than my laptop. I think I said that right. I'll give you another minute head start. I will be lazy and just use the function that we made. But try to do it manually if you can. That's very loud. All right, any questions come up as we were trying it? Were you able to understand what needed to happen? Make a bunch of predictions of slopes. It's for the sun's heights table using father to predict sun. And for 95% confidence interval, you want to read it off at the 2.5th percentile all the way to the 97.5th percentile, and that will be your range. Let's see here. Let's take a look. I am going to be lazy, and we will use the bootstrap slope interval function that we made for ourselves, which is what it's doing though, right? It's doing everything we need, right? Give me as many repetitions as we want. 2500 can be the default, and it's getting a bunch of samples of whatever table we give it, using x's to predict y's, right? Getting those slopes and calculating the correct percentiles to get the confidence interval that we want for 95%. This one is already set. This can be, so it's the sun sides table. We want to use father to predict sun, and we can use the default 2500. Let's go. And there it is, right? So it has determined that the slope of the best fit line through the data with 95% confidence is a little less than 0.4 all the way to like 0.64, which is decently wide. So we have some maybe hard data to predict for this, but our original data was like 0.5, but it's maybe not that correlated, not as heavily correlated as it needed to be to give you a very good prediction, because like 0.4 and 0.6, those are kind of far off from one another. So especially away from the mean, that's going to become a very wide range of differences. So that also just goes to show that it's there's more randomness at play when somebody grows up. It has to do with their diet. It's not just genetics, right? Not just genetics, but genetics are a big factor. And so we're trying to use genetics only to predict something, whereas there's probably more to it for height. But it was decently correlated. Yeah, so that was that one. And I hope you see what happened and what was going on. Any questions about that one before I give you one more? Next, I want to use serial. I want to use the serial data set. I think that'll be fun. So for the serial data set, let's use a bootstrap correlation, and let's do a correlation of something. Let's do, I think it was potassium and fiber that had like the highest correlated stuff. So let's use those guys, and let's do a 99% confidence interval, not of slope, not of intercept, not of prediction at, but correlation values. Because like for a different sample of cereals, the correlation between fiber and potassium might be different. So if we did bootstrapping, that would kind of cover that problem. That's interesting. That would be nice. Let's do that. And then let's also do a bootstrap prediction of, let's use fiber to predict potassium when fiber is 5, and we do a 95% confidence interval for the prediction value at fiber equals 5. How much potassium is there? What's the range? What's the confidence interval? So you can use the function for that one. But for this one, for the first one, you'll have to change kind of what we've done. So let's read in serial, and let's look at the original correlation of fiber and potassium. So here's our original serial table. It's not very large, so honestly, you probably needed more serials to do this well, but that's okay. It's just an in-class example. So the original correlation for fiber and potassium was this. 0.9 is very, very high correlation, but I want you to see, like, all right, was this just a fluke? What's a confidence interval? What's a 99% confidence interval for the correlation between potassium and fiber? Can you do that? So give that a try. So it's not slope anymore. It's not prediction at 99% confidence interval, which is going to be, which percentiles is that? It's like 0.5 to 99.5 this time, right? Try to do 2 of those. So one for correlation, 99% confidence interval for correlation between potassium and fiber. Again, you can use 2,500 samples. That's a good number for us. And then try to do bootstrap prediction using fiber to predict potassium when fiber is 5 grams, or whatever the unit was. Just do a 95% confidence interval for that one. Then you could probably use the function that we made. But understand what it's doing, right? It is making a bunch of bootstrap samples. It's calculating the prediction at that value. So yeah, give that a little try, and then I'll give you a head start and do it too. And let me know if you have questions. Hmm. Couple more minute head start. This is interesting. You can do a bootstrap interval to calculate kind of whatever you want. It's weird to think of correlation as something that you could like get a different value on each time, but yeah, it depends on the sample, right? So it's a number that depends on the sample. Of course that logged me out. I think that worked. Okay, sorry, it was making me log in on my other computer. Let's give this a try. Did this make enough sense? You see the process? It really is just one big process where you do the same thing, but just the things you calculate, and maybe the width of your interval is different. Yeah. So let's give it a try. Let's do 2500 again. So what I want to do, create 2500 bootstrap samples. Find the correlation values for fiber and potassium, and save them all so that I can get my interval out of everything. So can I copy and paste anything that I've done recently? Yeah, I can kind of do this one. Here. This is my prediction stuff, but we can change this. So instead of making predictions, I want to get a bunch of correlation values. Correlations, let's call it. Correlations. This is going to be a bootstrap correlation value, right? And the way that we get a correlation value is we just call the correlation function, right? We have a correlation function that took the table and the x column and the y column that we cared about. What's the x that we care about this time? It is fiber. The y that we care about is potassium, and it was abbreviated to that. And that should do it if I rename this to bootstrap correlation. Now I've got a big long array of a bunch of correlations. And this will give me a 95% confidence interval, but we want 99 for my example. And this is not for the prediction anymore, but for like the true underlying correlation of the what this should be. That'll be nice. So for 99%, it's not 2.5, 97.5. It's going to be, you kind of think of it as like, all right, 99 I want in the middle. So what's left of 99 is 1. And so I kind of want to chop the 1 up into equal pieces. And so I chop it up into halves. And so I go from 0.5 to 99.5. And that will give me the left and right ranges. And oops, it's not called table anymore. It's which table am I doing this with? It's the serial table. I believe that will make it work. And so if I just say left and right together, it will give them both to me. So for my original sample, the correlation was 0.90, but a 99% confidence interval using bootstrapping. Say like, all right, what maybe could it have been if I had different cereals in my sample? Make this more indicative of the true population of cereals in whatever year they were taking the sample, between 0.84 and 0.94. So it was a little bit off, but it was still very high correlation. Still a very high correlation. And that's what we're assuming. That's a cool answer. It's still highly correlated, even if we saw other cereals, most likely. Assuming our original sample was a good sample. Questions about that one? And again, we can make a little fancy graph of that too. We can say, let me paste it in because I don't care about you understanding how to make the fancy graph. Yeah, this one. Back to my code. Here's how you change up some of that code to print the cool histogram. There we go. And so again, here's our 99% confidence interval. You see how it's wider on the edges now. Wider on the edges. And it's a little skewed. So that kind of shows us that maybe our data's, we don't have enough data. It's not normally distributed maybe. It's just weird to think about. So yeah, we're dealing with fiber. And like, why is it skewed, you may ask? Let's do a histogram of all the fiber for our cereals. It looks like a lot of the cereals that we have are don't have a lot of fiber in them, but some of them have a lot. So I would say that the correlation values maybe are skewed to the right because when we took our bootstrap samples, maybe we cloned a bunch of high fiber cereals more often. Like they have a lot of weight. If we clone that 14 fiber cereal a few times, it has a ton of weight. And we do that enough, like maybe it ends up over there. Interesting to think about. But yeah, that's that one. And yeah, the other one was using fiber to predict potassium when fiber was 5 for a 95% confidence interval. And really, we can call the function that we made. But let's go look at the function again to remind ourselves what was happening. So bootstrap prediction. You give me a table, give me the x column, trying to predict the y column, give me the value you want to make the prediction at, number of repetitions you want to use, and we'll go and we'll make that many repetitions of predictions, right? We'll take a bootstrap sample, so a sample from the sample with replacement, just as many things. We will get a prediction for that bootstrap sample because it's a new table that looks like the original table. It's maybe more indicative of the population. Get a prediction at that place that we care about. Get a bunch of those predictions and then give me a confidence interval between them all. And so this is by default 95%, which is great for us. And so hopefully the process is like, it's becoming second nature. Like, sure, we've made all these functions, but I think you could do it too from scratch. So bootstrap prediction for the cereal table using fiber to predict potassium. Let's do, I don't know, fiber equals 5, x value of 5 we care about predicting for, 2,500 repetitions again. So for our original table, for our original data set, our prediction was exactly 173, read it off the line, 173-ish grams, milligrams of potassium, whatever it's measured in. And then for our 95% confidence interval, we're saying, all right, sometimes it could be less, sometimes it could be more, just because of the way we made our bootstrap samples. It could be, we're 95% confident that the true value for cereals in this era for 5 grams of fiber it's going to have this range of potassium values. 95% confident that's what's going to happen. And there was the histogram to prove it. Isn't that cool? So a lot of cool things can happen when you combine the idea of bootstrap sampling, because we don't know the true answer for any population. We can try to estimate it with confidence intervals. When you combine that with, we want to make a prediction of something, here's our original data set. Let's make a bunch of predictions from bootstrap samples. That's what we did. Okay, predictions of what? Could be slope, could be values read off the line, could be correlation values, all these different things. It's very cool. So yeah, I think that's what I wanted to say. Are there any questions about this process? Because that's kind of the majority of what I wanted to talk about today. You can use bootstrapping to get an actual estimate with a confidence interval of the true underlying line that we care about reading values off. It's really cool stuff. So yeah, I think one last slide and that'll be it for the day. One last question that we might have is, okay, we have all these random, we're saying that there is a real line. If we're going to use regression, we're assuming that there is a real line. We're assuming that the data is kind of kicked around the line just randomly through a normal distribution. That's what we're assuming. So we just get points and we're estimating lines. What if we see something that isn't there? So like, what if our data has been kicked around ever so slightly that makes us think that there really is something, but there really isn't? So here's the last question I want to leave us with. Like, what if we're just seeing the noise and the correlation really is 0? We shouldn't be using linear regression. We shouldn't be trying to make any kind of prediction at all. What if there is no real correlation, but in the noise we see a line that has a real slope? Yeah. So what's the likelihood that the slope is just 0? We can't make any conclusions, but we happen to see something away from 0. This is where bootstrapping can help us. Like, all right, give me a confidence interval of the slope, and let's see if 0 is within that confidence interval. Because like, if it wasn't in the original, it might show up in the interval. Does that make sense? That's pretty cool. So we could use confidence intervals, remember, to make to like test hypotheses. Like our null hypothesis is like, okay, the slope of the line is, the true line is 0. The alternative can be no, it's not. And we can give a 95% confidence interval to see where it is. Like if 0 is outside of that interval, then maybe it's not. But if 0 is within that interval, 95% chance we're right that it's there somewhere. So then we don't reject the null. That's kind of interesting. Let me show that to you. Let's see. So yeah, question. Last question of the day. What if the line is flat, so there's no correlation, you can't use one to predict the other, and there's no association at all? This keeps a data scientist up at night. So I had this original function, I'm just going to call it true slope is 0, true interval 10, sample size 25, let's say. So let's pretend this is what happened. All right, true line, let's say that the true line was 0. This is the true line through our data, but these are the random points that have been like kicked around just randomly through a normal distribution. Again, all we get was the data set. This is just an example of what could have happened, a nice function at the start that did that for us. You don't have to understand it. So like, this is the data that we get, right? We get to see this, and we're like, okay, maybe there's a little bit of a correlation. Let's try to do, we assume that there's a line that runs through this data. Let's use regression to get the best fit line through it, and we see a line with an actual slope. You see that? So this might happen one day. All right, here is our slope. Here's the best line through this data that we have right here, but it comes from an underlying distribution where the slope was meant to be 0, where there really was no correlation. Just got randomly kicked around in a way that made us see something, but that thing wasn't actually there. See that? That could happen to us. And the answer is, the way that you can figure out whether or not this was really correct or not is hopefully at a decent number of data points. And then you go and you do bootstrapping. You go and you get a confidence interval for the slope, because if the slope is 0, you can't make any predictions at all. So go and see if 0 is within the confidence interval for the slope, because bootstrapping might get rid of this line. It might make it go smaller, like it might make it go bigger, but in that case, it'll have 0 in the middle. Isn't that cool? So that will tell you whether or not these values are useful to do things with. A great example of that, by the way, if we go back to the births table, just for fun, we got a bunch of numerical things. Some things are just not correlated, like scatter. Maternal age, how old was the mom when she had the baby? Let's use that to predict birth weight, which doesn't make sense, really, right? You can imagine, like, all right, we're going to go look for clues. Let's see if there's anything here. It doesn't look like there's much of a correlation, right, between the age of the mother and how heavy the baby was when she had the baby. Didn't really matter. So if you go looking for a line, right, you might be like, all right, let's pretend. If you go looking for a line, you'll see one, and that has a slightly positive slope, yeah? Not much, but you're like, okay, maybe there's something. Maybe there's something there. So like, what is the slope? For that birth table, using maternal age to predict birth weight, maternal age on the X, birth weight on the Y, is like 0.095. It looks like the babies weigh slightly more if the mom is older. Crazy. You might think that that's true, but this is so close to 0 that it would be a good idea to do a bootstrap confidence interval. So let's do a bootstrap slope interval. We made a function for that, for births, for maternal age, for birth weight. Let's see what that tells us. Because our original one was saying there's something there. Slight, but it's there. This, again, will take a second. But when we get our interval back, do you see how sure it centers around here? But sometimes for our bootstrapped samples, we're getting negative slips around 0, probably not very exactly 0, but it's around there. So our 95% confidence interval for the slope of the true line contains 0. See that? Contains 0, which is telling us that maybe there is no correlation here. Maybe there is no correlation at all, whereas the original data set might make you guess and think that there is actually something slight when there isn't. So that's, again, a reason to do this kind of inference, to do this kind of estimation, because now we know what a 95% confidence interval means. It means 5% of the time we're wrong, but 95% of the time there might be a 0 here. So that means it's probably worth like taken more data at the very least. Go get more samples, see if this really wasn't just noise, but from what we can tell, it probably was noise. There's a good chance that there was noise in here, and it was just really zero. There was no correlation. You can't use one to predict the other. Doesn't make sense. And that's great. That gives us that ability. Whereas the original data set was like sending us maybe on a wild goose chase. But bootstrapping saved the day for us. It's like, the data could have very easily looked like this, where there was a negative slope and zeros in there in between. And so don't go making predictions until you've figured out whether or not zero is really there. All right. So yeah, that's the last thing that I wanted to say. Questions about that idea? So yeah, don't mistake correlation. Don't mistake a slight correlation or a slight slope for something. Go and do a test. Go and get more data. Maybe you need that. Yeah. And that, I think, is all that I wanted to say about this chapter. Are there any questions before I think there's one assignment that depends on this chapter. Are we ready for that? To assign that? So if we're good, that's the last thing that I've got for us. Homework 11, it looks like, depends on this chapter. So let's go give that a due date. Homework 11. It looks like, when are things due? So we're getting towards the end now. Homework 11. I want to do, I guess, okay, can't do the next week. Homework 10, Lab 9 are due then. Maybe the week after. So let's do the 6th. The 6th can be when homework 11 is due. The 6th of May. So that'll be the Wednesday. There we go. Now it has a due date. And I think that's all that I wanted to do. Any last questions about any of this process? I guess the moral of the story is bootstrapping can give us some cool facts about not just means and medians and things, but like can combine it with our other ideas like regression.